cycle dozens of students every week through this lab. Imagine training each one of them on the voice patterns. So that was one of the things that kept us a little bit back and said, well, we might do it in the future, but light is, click and go. So we went for that. Also, the deaf and hard of hearing, that's another important consideration. And we're going to be doing more with them. But we will do voice one day. I'm sure about that. This is what it looks like now. We have the assembly lines down here. We have the outbound area. That will be the pick-to-light system. The inbound will be the kitting. And we have an area here that has a mezzanine for observation with a little classroom. We have some students. I have the 3-4 students. They keep a desk. And we have a workshop to build some of the equipment that we need. We build a lot of in-house stuff. And it's very much reconfigurable as it is now. OK, assembly cases. We call them cases. They're the parts and the teaching that goes around the part. This is the flow of the system. This is the blood of the system. And we spend a lot of time in developing this. The real parts, like I mentioned, we started out with that thing up here, which is a radiator fan assembly. It's very simple. I got a company to donate those for us. And the complexity is only 7 parts and a couple tools. We've been using that since 2001, for a long, long time. So we're using those for some of the entry audiences, like freshmen and camps during the summer. But you have to keep in mind that to develop a case, we not only need a part or a bunch of them. We have about 50, 60 of those. But we also need to retrofit those for constant use. All of these that I'm going to show you are not meant to be assembled and disassembled hundreds of times. So you have to get them. You have to take all the self-tapping screws. You have to now thread those with steel. You have to change the type of screw that you're going to be using so you can actually withstand maybe power tool forces and do it again and over and over and over. And maybe you have to deburr the sharp edges, and you have to build fixtures, which is even more important. So the one on the top left is a fan assembly. This one is a minivan. Let me see if I get it right. Minivan, 3rd row seat, glove compartment. OK, that's the lid of that compartment over there. And it's also very simple. We actually were fortunate that one of the suppliers for Toyota moved or went south. I don't know exactly what happened to them, but one of their supply commodity engineers was a graduate student from the lab. He said, well, I got all these parts I'm sitting on. You want them? I said, well, it's simpler than what we're looking for, but send them. So we developed that. We try not to overlap. One of the things that I found discourages students the most is to do the same. Even if you have a different activity, if you use that in your freshman year and you see it again in the senior year, it's a turnoff. So we progress on different assembly cases throughout the curriculum. The ABS module was launched in 2006. It's a little more complex. And we use it in the senior level classes. This is one that just came in. We haven't launched this one. We haven't built any fixtures, but it's a water pump inlet assembly. So this is very important. We actually spend a lot of time finding those and developing them. We have turned away, literally, containers of parts. And one time, the very first time I sat with Toyota and say, I need parts. I said that loosely. Big mistake. They sent 2 truckloads of axles and windshields and ABS and airbags and things. Oh my God, what do I do with this? We ended up donating all that to the scrap metal recycler. I turned that away, and I could only get one thing out of the whole container. So we're much careful now about what we wish. Usually, we find a need. Like we have a graduate course that doesn't have an assembly, or we have a particular exercise that needs something that is more difficult to assemble because, I don't know, maybe they're mechanical engineers. They're more interested in the mechanics of assembly, but it has to be power tool capable. So we talk to Toyota. We make a trip. We look at the parts. We may actually make a round of with either the suppliers or within their plants. And finally, we try to secure the shipment, once it comes, you still have to, like I said, build the fixtures. So these are actually some of the communications with Toyota on going back and forth on the parts. These are fixtures that we have built. And you have to then try to buy maybe some spare parts, some of the O-rings, some of the screws get lost. So you buy more than come with the parts. And like I said, you have to really work on the fasteners because none of these are meant to be assembled and disassembled many times over.
How many assemblies do you need to be able to inspect?
It depends on the cycle time and the activity you want to do. So for example, if I have something like this with a power tool, you can assemble that in less than a minute. If you're going to run the line for half an hour, you need 100. We usually have a disassembly at the end so you can fit parts back. But if you're going to do something this complicated, that's a much longer cycle time. You can run half an hour, you're not going to make more than 10. So it depends on that relationship between cycle time and I think that's what you're doing too. Sometimes you're working on parts presentation at the workstation design. You don't need to run the line, so you only need one part per station. So let me jump into the curriculum. I think I have about 15 minutes, so pick up the pace a little bit. We have ended up serving quite a few courses because it is attractive to have a lab where you can take your students, and we're very open to let other disciplines do that. We serve the freshman courses in IE and mechanical engineering and NTID, the Deaf and Hard of Hearing Institute. This is a senior course in IE, and these are graduate level courses, mostly lean courses in a couple of departments of engineering as well. So, and these are the credit-bearing courses, the one you get credit for, students do. So you can see the span of disciplines and also throughout the years, curriculum, and also how many experiences. So in this class, the practicum is obviously a lab-based course. They come 10 times. Every week they come. We're in a 10-week quarter. In this class, which I teach, they come 9 times. They really come 10, but I keep a buffer so that we can spill over if we go too long on a certain topic. So they come every week to this lab. Some, you have some slack, or some faculty actually decide to do some of the things. The intro, obviously, this is only a portion of an intro to IE course. So they spend 2 weeks here. They might go to an ergo lab for another 2 weeks. They might go to some other place for a couple other weeks. What we try to do is think about now, and a lot of this was done in retrospect, but is what do we want the students to be? Do we want them to be an observer? So we have that observation level. That's typical for camps, short experiences, 15 to 45 minutes. If they want to come, maybe we have our own students, our own staff, act it out, and they just look. And of course, it's facilitated, and faculty can just drive some questions. This is great for some of the quick tours and folks that don't spend too much time. You can look at where we hit in the Bloom's taxonomy. If you have a little more time in some of the courses, you can hit the operational level. You're giving the students a design. You're going to work in a 4-station line, okay, with 3 workers, and you're going to share stations, and you're going to have a demand that looks like this. Go. So they work on that environment. And then you might propose an improvement, or they might propose an improvement, so on, whatever the activity actually is about. Or in some of the more advanced courses where you want them to analyze, synthesize, and evaluate, you give them a free slate. This is your demand. You tell me what the system looks like. And they design it. And then they implement it. Reconfigure that, perform, and compare. And again, improve. So we try to do sometimes this cycle many times just to drill down. Sometimes we actually are able to score the economics of a system. You have so many people working so many hours. You have so many tools, so many parts, weight levels, and so on. It's costing you $10,000. Can you do it for 5? By the way, I'm going to increase the takt time 50%. It's going to come faster at you, so because we project the demand. It's popping at them. And then they do it, and I just barely made it. You know what? Next week, you're going to do it again. You're going to slash it out to 2,500, and the tag is going to come faster at you. So they have to do it again. And that's usually pass or fail type of, you make it or not. So that forces them. You get a 0, you get 100. If you meet the takt and the demand and the cost implications. And when they do that, it really forces them, that pass or fail scenario, to, offline come to the lab and think about it. Then they have to usually document it in an A3 and present it quickly. So this is what we're going to do. And so how we're going to achieve this. OK, I'm going to skip that. So this is the cycle that I commented on as far as teaching the content, letting them design and predict, prototype and implement. Then they're going to perform and assess. And then they have to problem solve and improve. And then they do it again, multiple times. My course, the one that I teach, it's a senior level. We go and progress from understanding the diagrams, the parts, the disassembly, to line balancing on week 2. We do a quick production run. We do a quick balancing through Yamasumi charts, the stack charts. And then I do a quick reporting. Then finally, week 3, we run a mass production scenario for a longer time. And I tell them, you got to produce as much as you can. So bottlenecks pop up, accumulations, idle time, high utilizations. They got to document all that. Comes an analysis. We do a little bit of virtual factory playing as well. Then we stage 3 parallel systems. We stage a bucket brigades, okay, with 3 people versus 3 independent lines with 1 person each doing it all. And then we also have CONWHIP, where we actually restrict with Kanbans, you restrict the work level to 4 and then to 2. And we compare that in many aspects, from economic, from all the way to productivity metrics. We have a lab where A3 is emphasized. This is the plan, do, check, act improvement methodology. And then this is the challenge that I told you. I'm going to give you a demand. You have to meet this particular productivity, throughput, cycle time metrics. And the next week, they're actually asked to do it faster, quicker, cheaper, and again and again. So 3 or 4 times as well. The 2 graduate level courses are more based on lean and TPS concepts. And perhaps some of the inheritance issues, Kodak actually developed a Heijunka box system that was more complicated than Toyota's. And one of the person behind that is in our faculty now. So he teaches a 4-box Heijunka approach to production leveling, and those are all homemade and boxes just to level the production onto the floor, from the demand incoming all the way to the station. And the students walk the carts and walk the flow, and they place them in the right locations. And sometimes they give them a snapshot. What does the box look like? So they have to go and place the carts where they go. It's actually pretty interesting and more complicated than I thought it would be. We don't have audio, so I'm going to skip that. Maybe towards the end we can show that. Let me just quickly talk about corporate relations and communications so that I can show what also rounds up the environment. We maintain close communications with a number of companies. And then we have targeted some of the companies we want to be closer to. Obviously, Toyota Motors Engineering Manufacturing North America, TEMA, out of Cincinnati, Erlanger, Kentucky, is a company that makes cars. Now, Toyota is very big.